talk is going to be given by Enrique Román-Calvo on arbitration-free consistency is available and vice versa.
Thank you so much for having me. This is a joint work with Hagit, Attiya, and Constantin, Enea. And in this work, we focus on storage systems because storage systems appear in our daily life. For example, imagine that you go to a conference, like in Rennes, and you need to book a room. Then most of us do it using some application that internally has some storage that reads that the room is available and then writes that the room is no longer available, I just booked. And this diagram with application and storage is very easy to understand, to imagine how the structure of the application looks like, but it doesn't really apply to real implementation. Like if you think about a real implementation of storage systems, they look more like this. Instead of having all the information stored in a single place, in a monolithic scenario, we have a distributed system where the information is distributed across different replicas connected through some network. So at the end of the day, all the information is available, but the access to the system doesn't become a bottleneck. The system is not often distributed, but also replicated, meaning that the same information may appear in 2 or more different nodes. That makes the system more resilient in case there is a crash of a failure of the system, right? Because if some node crashes, you can still retrieve information as a backup server. And those distributed replicated systems are great, right? Because you improve the performance, you make it more resilient until you actually have to use them. Because one of the main issues of distributed replicated systems is consistency. We expect them to guarantee some notion of consistency, and it's not always trivial, right? Let me show you with this example. We have 2 clients that want to book the same room. So for example, we have some client here that use the application and book the room. The update applies to the replica it connects, and the updates on a replica doesn't immediately transmit to the whole system. So there is a moment in time when the system has 2 different versions of the same information, one that the room is available and the other that is taken. When the second client tries to book the room, we expect some notion called strong consistency, meaning that the client observes the latest version, so the room is taken, right? But what it can really happen is that the information that the room is taken arrives later to the client that the room is free due to some problem in the network. So at the end, the second client observes that the room is still free, so book it. And unless they are friends, they will have to share a room, which is not an ideal situation. Actually, talking about ideal things, we could think about what are the properties of an ideal storage system. We just mentioned strong consistency, the property of strong synchronization between replicas. As other ideal properties, availability, meaning we want to reply to our clients immediately, don't have to wait for the network to coordinate. And the third property is partition tolerance. That means that in case of there is a crash on some replica, we'll still be able to reply to our clients. Unfortunately, the CAP theorem says that you cannot have the 3 properties at the same time. In fact, partition tolerance is a not negotiable property because in a distributed systems, replicas may and will fail due to the nature of the system. So there is always a trade-off between availability and strong consistency. Sacrificing availability means making our system slower because we have to synchronize. So it's often the case that instead of providing strong consistency, we provide weaker notions of consistency. So what does it mean to provide weak consistency? Let me show you with an example. Here on the left, we have a program with 2 clients, one that writes X and Y, and the other that reads X and Y as well. Under strong consistency, we expect the clients to observe the latest version. So the executions are essentially like this, like the first client, let's say, writes X and Y, and the second client observes both writes of the same of the client because they have to observe the latest version. On a weak consistency, clients don't necessarily observe the latest version. They can, but they may not. So for example, under some notion of weak consistency, an execution like this can actually happen, where the first client is executed, but the second client only observes the write on Y. The write on X may not be visible due to some problem in the network, right? And this is not an admissible behavior under strong consistency. A particular case that you may be familiar with of consistency is called causal consistency, where we expect information to be observed transitively. So for example, this case, where the second client observes y but not x, is not valid under causal consistency, because if you observe y, the write on y, you should also observe the write on x, because the write on x happens before the write on y. That's the notion of transitively. However, under causal consistency, you could still observe phenomena not admissible under strong consistency, as we saw here, where you observe the write on x but not the write on y. So causal consistency is a particular case of weak consistency, but one can imagine that there are many other models. And why do we care about weak consistency? Because the thing is, even if we have a strong consistency that you cannot implement it in an available manner, causal consistency you can actually do. So there is always a trade-off between the consistency that you provide and the properties that your storage system can have. So in this work, we focus on which class of consistency models can be implemented in an available manner in the case of a network partition, in the case of our system that has to be partition tolerant. And we focus in a very general scenario when we have multiple operations, right? Because when the application uses a storage system, the storage system may impose some requirement, like you have to use some particular API that can go from simple put and get operations that read a single object or write a single object, to more complex operations like SQL that can affect you an unbounded number of objects on your system. And I said that we have to focus on the operations because there are particular consistency models, that this one I present here, the conflict-preserving causal consistency, that on simple operations like put and get, you can implement in an available manner, but on more expressive operations like SQL, you cannot do it. So this problem is actually hard to resolve. So just a quick recap in case I lost some of you here. What we have here is an application that communicates with a distributed system that we assume there is partition tolerance from here onwards with some operation. And in the middle of this, we have a consistency model that talks about the semantics of these operations. And then we can ask ourselves if the system can be available or not. Okay, good. We are actually not the first one investigating those results, as one can imagine. Like for example, here, there were two independent groups, Mayahan and others, and Attiya and others, that found two independent, incomparable conditions for a multi-value store to be implemented for not being implementable in an available manner. While beyond those negative results, as we mentioned, causal consistency can actually be implemented in an available manner for the particular case of the key value store, right? But the problem of those results, where they are nice, as the title of the slide says, they are partial results. They don't answer completely the question. There is not truly answer to the question. Well, until now. What we present here is the arbitration-free consistency theorem, a tight characterization, an if and only if condition that says when an implementation can be available, can admit an available implementation. And this condition that we found, arbitration-freeness, that we'll present in a second, has a nice corollary. They said that the strongest that one can implement is causal consistency, meaning the positive result I just presented, it coincides with the best that one can do. And that actually corresponds to the intuition that the distributed community had, that causal consistency, you can implement it, and anything else is probably not. Okay, so this is what we prove. Let me show you what this condition exactly means with, again, the recap. This is where we are. The application, the system, and then we ask if we can do it available or not. Okay. So, as we said, the corollary said that you have like a strongest model that one can implement. Hence, we first have to talk about all possible consistency models. And for talking about all consistency models, you first have to have a framework for defining consistency models. For us, a consistency model is a set of visibility formulas that indicate when some write instruction, like a put, is visible to some get instruction, some read. And we say that the put is visible to the get if there is a change of path dependencies, a sequence of events that has to happen before between the put and the get, so the put is actually visible. And this change of dependencies, it may involve, for example, a session order indicating that something happened before another instruction if they execute the same replica. Or, for example, read dependencies that once something is happened before other if something is written, or even writes an object that is written by someone else. We can also model communication we received before to model that some instruction has to be received before executing a second one. And we can also model in our framework arbitration. Arbitration is a particular specific relation that it's on a slide. And basically, it's a total order between events that acts as a tiebreaker in the case of concurrency. So to put an example, imagine that you have two put instructions and you have some get that should read from somewhere, right? The arbitration tells us where you should read from. So for example, if the second put happens after the first put, then the get will read value 2. Well, if it's the opposite, then it will read value 1. This arbitration is like a last writer wins a conflict resolution policy that it's a global order, as I mentioned, and it's often using different models to exactly for this reason. But not always, right? Other conditions that I presented, like received before, possession order, etc., they are not global properties, they are local properties, because you can essentially depend on my replica, my instruction, what I observe or what I don't. So it makes sense to distinguish between those models that depend on this global order and those models that only depend on local information. And that's the exact condition that we have. The arbitration freeness is a condition, say a model is arbitration free, it can be defined with as arbitration. For example, causal consistency is arbitration free because it can be defined only using communication, while sequential consistency, a weak version of a strong consistency, it's not arbitration free because it always requires this arbitration. This definition is nice, it's cute, but it's not only that, it corresponds to the exact condition that we found in our theorem. Because, and basically, it makes sense, like the causal consistency or corresponds to the intuition that causal consistency you can define with arbitration and you can implement it with, in a available manner, sorry, whereas sequential consistency, you cannot do it and it's defined with arbitration. So now we know what we want to prove, now we know the condition that we found for the proof. Now let us go to what actually the proof works. Well, a very schema of that. As an if and only if condition, we can, the proof is divided in two parts. Okay? The first part, showing if the arbitration free is available, the first part of the title of our paper, is actually pretty simple. Because if our model is arbitration free, one can prove that it's actually weaker than causal consistency. And causal consistency, we know that you can implement it in an available manner. Therefore, an implementation of causal consistency is an implementation of your arbitration-free model that you want to do. So that's the easy condition, that's pretty easy. The hard part is actually the vice versa condition, that showing that the model is, that the implementation is available, your model should be arbitration-free. And actually, we prove it the contrapositive. So if it's not arbitration-free, then it's not available, and that implication we prove a contradiction. So it's a bit complicated, but basically what we have is implementation that is available, but that provides a non-arbitration free, and we show that this scenario is impossible. Try to find a contradiction. Okay? I hope I didn't lose you so far. And basically, this is like a bit of a sketch. Because your model is not arbitration free, we can construct a particular program that will lead to a contradiction. And basically, because your model is not arbitration free, there is a visibility relation that uses arbitration. Makes sense, that the model is not arbitration free. With that visibility formula, we construct a program a la CAP, meaning inspired by the original CAP theorem proof, that if in the case, for example, here they have a visibility with n+1 events, then your program is executed on two replicas, each of them with n+1 events. But there is some kind of symmetry here to make the construction work. So basically, the first part of the events before the arbitration is executed on one replica, and the other part of the events are executed in the second replica, and vice versa. We require that the first instruction should be a write instruction, the last instruction should be a read instruction. The instruction in the middle depends on or in the definition of your visibility, but you can always find something. And we require, and that's important actually, that if your last instruction is a get on X, no one in your replica will write on X. Only the opposite replica can write on X, but yours cannot. With that idea, with that particular construction, then we can show actually the contradiction. Because if our model is, your implementation is available on partition tolerance, we can observe that it's partition tolerant, we can assume that there is no communication, right? Because the network can be totally disconnected. And then, yet an unavailable implementation, all instructions have been executed. Hence, you have a trace with all instructions executed and no communication happened. In that scenario, the get on X here must read X from somewhere. It cannot read it from the first replica because no communication has been transmitted. It cannot read it from its own replica because no one writes on X. So it should read from the initial state. Okay? And once you have that, we observe that by the particular construction that we found, the put on X1 is actually visible to the get. Right? You see this green and yellow path. Hence, we observe that the get on X does not read the latest visible value. And that's a contradiction, because we expect that instruction should read the latest visible value, and this is not the case. And that's basically the whole idea of the proof. For a general setting, where you have more expressive consistency models, more expressive operations, the proof is essentially the same but more complicated. But the details are in the paper. So let me already conclude with what I show here. The arbitration-free consistency theorem is the first type characterization. It's an if and only, a true if and only if condition of available implementation. And the condition that we found is essentially a syntactic condition. You define your model with the grammar I presented, then you check the definition, and if it's arbitration-free, you know that it can be implemented, otherwise it cannot. But this is not the end. There is more future work. For example, we know that this is the way to check arbitration freeness, but can we automatically check it? Well, that's actually not that trivial, right? Because the definition of the model, taking into account the operation, can be really convoluted. So we don't know yet how to efficiently do it. And another interesting and theoretical question that one could ask is, well, the CAP theorem is a well-known theorem studied in the database courses. And we managed to generalize using this way of thinking. Maybe we can do the same with other well-known results like pass-out or count theorems. Maybe we can get something else out of it. I don't know. We'll see. That's future work. But well, that's all for me. Thank you so much. Happy to have questions.
Okay, great. So we have a bunch of time for questions. Does anyone have any questions?
So thanks, great result. I guess my question is a bit high level. So there are other interesting things happening at the level of causal consistency if you compare to stronger and weaker models. For example, you have consistency checks becoming polynomial time. You can also define these models in monadic second-order logic. So I wonder if, for example, one could explore MSO as a specification language for the available systems, or maybe relate arbitration freeness to polynomial time consistency checks. Have you thought about this at all?
For the first part about monadic second order, honestly, I have not thought about it. For the other part about the polynomial checks, yes, but I'm not quite sure if there can be a connection, right? Because I mean, at least the results I know about polynomial consistency do not talk about communication. So I'm not sure how the results apply first in the communication setting. I think the receive before relation is not always modeled in those results. And if they do, maybe there is a relation there, but it depends also on the scope, right? Do we care about communication or not? It's interesting, absolutely sure, but I cannot confirm that there is a link that can be polynomial, if and only if it's arbitration-free. I wish for it, but I can't.
Right. It just seems very peculiar that many things start happening, like coinciding at the causal consistency level. So I guess it would make sense to try and look into kind of some unifying theory around that level?
Yeah, it absolutely would be interesting. I wish I could have the answer, but I don't have it yet.
Thank you.
So does the corollary, like, would this actually be an implementation strategy to get the, or do you think it's too impractical to actually build and run?
I mean, I'm like not sure, right? Because, for example, you can like the first part, like if it's arbitration-free, you can implement it. Basically, reduces to implemented causal consistency. So that gives us nothing for anything that is weaker than causal consistency, at least in the part of our result. For anything that is stronger, not so sure, right? Because, for example, knapsack isolation or parallel isolation in the case of databases, they are like efficient ways to, try to overcome this problem. Yet, like in the case of our results, they are grouped all the same category bad implementation. There is no available implementation. So I cannot see why, but maybe there is a way. I just don't know it.
So I have a naive question.
Okay.
In the intro, you said you talk about an example with the booking and the room, and so I'm guessing this does not apply to this example, or if so.
Can you say it again? Sorry.
I'm guessing this was an example where the conditions were not met.
Oh, so sorry. Can you say the whole is a question?
I'm trying to understand so I don't know much about this.
Okay.
I'm trying to understand in practice
Mm-hmm.
on the booking example, if you wanted causal consistency to be applied, what would it look like?
And you could have causal consistency on at the end you might, like the case of a booking is a database that uses some SQL operations, and then on top of that you can enforce causal consistency as a model. So you have your operation like SQL, let's say, with causal consistency, and then the application will say SQL with causal, and then you could implement it. Actually, there are real implementations that can enforce those conditions. If that answers your question.
I think so.
Okay, no, we can take it off. Okay. Yeah, no, thank you.
Hi, thank you for the great talk. So as far as I understand the results, it relies on these kind of visibility relations for the definitions of the models.
Mm-hmm.
But I guess you could define a model like in a more complicated manner that doesn't use these visibility relations. Do you have any feeling of whether the result would generalize to a more general definition of these models?
In its all generality, it will be complicated. I think intuition should still hold in some way, because the drawing is really easy, right? So I expect in some way that it will hold, but of course technically tests can be really complicated. The thing is, the first thing we think, like, which model is used in practice that cannot be defined with this framework. Like, so far for my knowledge, that is limited, all the models that different objects can have are already captured here. But maybe there are other interesting models that we cannot capture, and of course, one could think about it.
Okay, so we can take one or two more, but in the meantime, can we have the next speaker come set up? Okay, if there are no more questions, then let's thank Enrique one more time.